All right, so I'd like to go over a couple of problems that will help you with the homework um, that are also, in some respects, solved in a similar way, even though they look like very different problems. In this first one, we have, um, or we're trying to find the tension in each string, and two of the strings are at angles, so we need to break it into its components. So first off, I'm going to label this one T1 and this one T2, and then draw in the components. Now, these tensions, they're holding up this block, so basically they're pulling in these directions. And in components, I'm going to call this FH1, which is pulling to the left. Here's FV1, pulling up. Over here, we'll have FV2, pulling up, and then here we have FH2, pulling to the right. So the two diagonal tensions are pulling at angles, and we jump into component vectors, by the way, just due to right triangle geometries. This angle here has to be 22 degrees, and that angle there has to be 49 degrees. It's basically alternate interior angles. And then finally, we have the third string, which I'm going to label T3, and it's holding onto the block, which of course has to have a weight. And so now I have a picture of all the different forces, including the directions that they are pulling towards in the diagram. If I just consider the block by itself, nothing is moving. And so for those forces, the F net force, well, it's got T3, and it's pulling, holding up the block. Of course, the block has weight, so that's going down. And again, nothing is moving, so there can't be any acceleration. Therefore, there's no net force. This will lead us to, of course, T3 equals Fw, which would be mg, which would be the 22.7 kilograms times the 9.8 meters per second squared. And so T3 equals 222.5 newtons. And again, we're just focused on this one's pulling up, that's pulling down. So for the block itself, which isn't moving, it's got two forces applied to it. The tension in T3 upward has to equal the weight downward, and that's 222.5 newtons. Now we're going to focus on this portion of things. In other words, all of this, the string, which are basically considered massless, and the block, these two strings are holding all of this up. So again, if I think in kind of an x direction, since these guys are at diagonals, if I think of an x direction, well, in the x, the only things going x, and we could put a little diagram right here just off to the side to help us. So y and x for our directions. So if we're looking in the x direction, the only forces that are in the x direction are FH1, the horizontal component of T1, and FH2, the horizontal component of T2. And for those things, they also have to sum to 0 because nothing's moving. And so whatever force this is going that way, but this force going that way because nothing is moving left or right. Which of course then means that FH1 and FH2 have to be equal but opposite in direction. Now, we can actually determine these components a little bit more detail. In other words, this is the horizontal component of this diagonal, and using cosine, basically FH1 will be T1 times the cosine of 22 degrees. T2, or FH2, will be T2 times the cosine of 49 degrees. But I don't know T1 or T2. That's part of the problem, figuring out what T1 and T2 is. So I need some more information. Well, as I mentioned, nothing's moving, which means this whole piece, the string and the block, they have weight. The two vertical components have to be holding that weight up. And so I can do my net in the y direction, which is going to be the vertical component of T1 and the vertical component of T2 minus FW, because it's the only thing that's going down, and all of that has to be 0. And I can, start playing. So I'm going to have for FV1, well, that's the vertical component of T1, so that's going to be T1 sine of 22 degrees. And then T2 sine of the 49 degrees. And of course, together, they're going to equal the FW, which is mg, which will be the 222 times the 9.8, or the 222.5 newtons. Now, if you're like, why did I make this one negative? Well, I made it negative because one's up and one's down. All right, so now I have one equation with T1 and T2. I have a second one with T1 and T2. Everything else is basically a number. And so I can do a substitution for either T1 or T2. So, for example, I can, basically take the this equation here and go, all right, so T1 is going to equal negative T2 cosine of 49 degrees, and all of that will be divided by the cosine of 22 degrees. And that's going to give me basically a negative 0.708 T2. And then I can take that and plug it into the equation right above it. So take this and plug it in for my T1, and then I'll only have T2. And so basically with negative 0.708 T2 times the sine of 22, which is 0.375, plus sine of 49 times T2, which is basically 0.755 T2. And again, all of that has to equal 222.5 newtons. Now, all of this will be, when I do this and do that, combine them together, they end up with 0.49 T2 equals 222.5 newtons. So that'll lead to T2 equaling 222.5 newtons divided by 0.49. And so T2 is going to be 454.1, about 454 newtons. Which then I can use that back here where I have T1 related to T2. And so I'm going to have the T1 equals the negative, and again, in this case, the negative is just the opposite direction, the negative 0.708 times the 454 and so I get 321.5 newtons. And so up here is the tension in T3. Here is the tension in T2. And I left off the negative sign because that's just directional. It's to the left, whereas T2 is to the right, but the tension in T1 is 321.5. And so we have found the tension in each string. And really, it all comes back to the net forces, either horizontally or vertically, have to add up to 0 because nothing's moving. Now, in the second case, we have two masses, M and big M. They're connected to the same string. It passes over a frictionless pulley. If we consider them to be initially at rest and then they're allowed to move freely, well, the bigger one is going to pull down. In other words, it's going to move that way, which of course means that the smaller one will move up. And we can consider F nets for each side, if you will, of the pulley. There's a tension. In other words, that's a force that would tend to pull upward. And then that would tend to pull downward. And so now, independently, I have all of the forces that I have to worry about. So I'm going to do this in two parts, the left side and the right side. First for the small m. So F net for the little m. Well, again, I'm assuming this one's bigger. It's going to pull down, which means this one's going to pull up. So T, it's going to be more than the weight. There is a net force in this case because things went from rest to in motion, and they're going to speed up the further they move. And so, since there is a net force, we can say that about this mass as its mass times its acceleration, F equals ma. Then, for the right side, for the bigger mass, well, in this case, since this is moving downward because it's heavier than that one, it's going to be greater than the tension. And so I could write it this way. But it's also got an acceleration. Two things I don't know. I don't know the tension in the string, and I don't know the acceleration of the masses. All I'm saying here at this point is that whatever the tension is in the string, it has to be the same because it's the same string all the way around. And however the masses are moving and accelerating, it's all connected. So it's moving down with a certain acceleration. This one's got to move up with the same acceleration. Similar to what I did in the problem above, I can now do a substitution to solve for the tension or the acceleration, and then use that to find the other one. So let's go ahead. Pretty simply, I'm going to take the top equation and rearrange it for t. And these are all lowercase m's at this point. But now I can take that and put it into the second equation. So I'm going to have mg, the bigger mass, minus okay, again, this was this, then I substituted in here, and that has to equal the big M times its acceleration. Now, what I need to do is solve for the acceleration in this case. I know the masses, they're listed right here. I know what gravity is. The only thing I don't know are the accelerations. So I need to do a little bit of algebra. So first, and then I'm going to move the MA term to the other side. Then I'm going to factor. So over here, I'm going to have m minus m, capital M, the big M, minus the little m, g. And on this side, I'm going to have big M plus the little m times a. And now that I have it in this form, I can rearrange everything to solve for the acceleration. And basically, the acceleration is going to equal that, in which this ratio, which is divided by the sum of the masses and then times gravity, this ratio will be true all the time for this problem, no matter what the masses of little m and big M are. And again, we just have the one assumption that capital M is a bigger mass. So, hey, we could go ahead and plug in our numbers. Our bigger mass was 180. Our smaller one, 120. The G here is for grams, it's not gravity. And then all of that's times gravity. And 180 minus 120 will be 60. 180 plus 120 will be 300. So basically, our acceleration is going to be 1/5 g. And since I now know the acceleration, I can come back up here to find out what the t is. So t will equal mg plus m times 1/5 g, which basically is going to be 6/5 mg. For our acceleration, basically a is going to equal about 1.96 meters per second squared. That would be 1/5 g. Our t, on the other hand, the tension in the string, okay, that's going to equal, let's see, our mass was, for the little one, was 120, which, if you divide, we have grams here, so grams divided by 1,000 to turn it into milligrams would make it 0.12, and then, of course, times gravity. And our t here was basically 1.41 newtons. So there's our acceleration. And here is our tension. So both of these solved with basically two equations and two unknowns. However, do not be surprised if on an AP test, whether it's a multiple choice or a free response, that instead of your answer meters per second squared or newtons, that the actual answers would be in terms of g or in terms of mg for what you've got going on. And so, two problems in which you have to basically do two equations and two unknowns, do a substitution to solve for one, and then substitute it back in to solve for the other. Kind of like really different looking problems, but on the other hand, by looking at all the forces involved and looking at the net forces in problem one, nothing's moving, so the net force has to be 0. In problem 2, things are moving, and in fact, since one of them is falling and pulling the other one up, it's all connected, they have to be accelerating. So, that's your homework.